Welcome to this explainer. Today, we're diving into a complete introduction to geomorphology. We're going to cover its meaning, its nature, its development, and the overarching principles and scope of the field. Basically, we're figuring out exactly how the landscapes around us are formed, measured, and understood. Let's get right into it. Here's our agenda for today. We'll start with what is geomorphology, move on to the geomorphological revolution, then cover the principles of geomorphic systems, the scope of geomorphometry, and wrap up with applied geomorphology in society. Section 1. What is geomorphology? The meaning and nature of the science. So the crucial point here is that geomorphology isn't just about looking at a mountain and saying, wow, that's a nice mountain. It is a totally dynamic study. We're looking at the actual raw materials that make up the Earth, the physical and chemical processes molding those materials, and how that landscape naturally evolved over time. You could actually break this science down into a really simple 4-step framework. First, identifying the physical form. Second, analyzing the materials, the dirt or rock. Third, measuring the specific processes shaping it. And finally, tracing its historical timeline to see exactly how it evolved into what we see today. Section 2. The geomorphological revolution, from historical theories to quantitative science. For decades, a model known as the Davissian cycle totally dominated the field. William Morris Davis categorized landscapes pretty simply as youthful, mature, or old. He essentially treated time itself as the only process. But modern geomorphologists realize something massive. Time isn't a process. Time doesn't erode a rock. Water and wind do. So they realized they needed a deductive, math-based framework to understand exactly how things change, measuring actual cause and effect processes happening in the real world. This brilliantly illustrates that huge shift. On one side, you've got the old inductive route, which essentially took unordered facts, classified them, and kind of just guessed at a law. But on the other side, you see the modern deductive route. This completely replaced the old method with a rigorous design. We're talking formal models, hypotheses, exact data collection, and strict statistical verification. It literally turned geomorphology into a true rigorous science. Just look at how this builds over time. Starting from those early descriptive theories in the late 19th century, we transitioned through the 1940s and 50s. That's when scientists like Horton and Strahler sparked the quantitative revolution, replacing basic descriptions with hard math. And that leads right up to the 1970s and beyond, bringing us to the modern era of systems theory and advanced mathematical modeling. Section 3. Principles of geomorphic systems. How landscapes find their balance. The geographer D.R. Stoddard proposed 4 reasons why systems theory is basically the perfect organizing principle for geomorphology. But the absolute most vital takeaway here is that last point. Landscapes function as dynamic units that use negative feedback loops. What does that actually mean? Well, it means natural systems inherently work to maintain stability. Whenever a change happens, the system pushes back to resist catastrophic failure and find its balance again. Looking at Shum's models of landscape evolution here, we can see how this plays out over literally millions of years. Modern science shows us that landscapes don't just experience some slow, continuous, smooth decline. Instead, they exist in what's called dynamic metastable equilibrium. Think of it kind of like a Jenga tower. It stays stable for a really long time until a threshold is crossed, resulting in an episode of abrupt, sudden adjustment before it finally settles into a brand new level of balance. Section 4. The scope of geomorphometry. Measuring the Earth's surface. Now, the scope of geomorphometry is generally divided into 2 main strategies. On one hand, we have general geomorphometry. This is used for mapping vast, continuous, rough surfaces, like entire drainage basins or mountain ranges, without really worrying about individual features. But on the other hand, we have specific geomorphometry. This approach isolates and measures individual features based on strict criteria, like measuring the exact angles of a single sand dune or a glacial drumlin. But here's a wild thought. The objectivity of all this math can actually be an illusion sometimes. Check out this surprising quote. It turns out you can find mathematical patterns anywhere if you look hard enough. The mathematical relationship used to describe branching streams works just as well on the veins inside a cow's liver. Crazy, right? So, the crucial point here is that quantitative measurements are only valuable in geomorphology if they actually relate the landscape's form to a specific, real-world physical process. When we do correctly connect form to process, though, the results are incredible. Geomorphologists can use these specific measurements to essentially act as Earth historians, post-dicting past climates. For example, finding and measuring a pingo, which is a very specific mound of Earth-covered ice, proves the past existence of permafrost. Or analyzing the shorelines of closed lake basins can literally tell us the exact precipitation levels from thousands of years ago. How cool is that? So, after covering the history, the math, the models, and the measurements, we really have to ask the most important question for us today. How do we actually apply this science to the real world? Like, why does this matter to you and me? Section 5. Applied Geomorphology in Society, Predicting and Preventing Environmental Disasters. Mapping out active landslide zones near coastal areas perfectly illustrates how scientists translate all that complex data into vital hazard predictions. By deeply understanding the slopes and materials, they can map out unstable areas to protect roads, vital infrastructure, and ultimately human lives. It's a real game changer. The ultimate application of this science is mediating between two clashing systems. Remember those natural physical systems we talked about earlier? They use negative feedback to self-regulate and maintain balance. But human intervention systems, think mass agriculture or heavy construction, are often dominated by positive feedback. This means our changes accelerate, break natural thresholds, and can literally lead to system destruction. A prime example of human-induced positive feedback completely destroying a landscape, the devastating U.S. Dust Bowl in the 1930s. And that brings us to a final thought to ponder. The Earth has mechanisms to find its own balance over millions of years. But as our understanding of geomorphology deepens, we really have to decide, will our modern interventions be thoughtfully regulated by this science, working alongside natural systems? Or are we going to ignore the models, trigger catastrophic positive feedback loops, and engineer our own collapse? Thank you so much for joining me on this explainer. Keep questioning the ground beneath your feet.